This is a short introduction to the notion of function notation and the idea of composite functions. So look at these two functions. They're the same thing. One says that y equals 2x plus 1, and the other says that f of x equals 2x plus 1. Now, y equals kind of has a disadvantage, because let's say that I want to talk about several different functions. You're used to thinking of y as that range element, so we tend to write y equals whenever we're doing functions. Now, this could be confusing, because if I refer to any of these y's, you're not quite sure which function I'm talking about. So, when we use this thing called function notation, things are a lot safer. These are advantageous. So I can say that f of x equals 2x plus 1. Then I can say that g of x equals negative 3x plus 4, and that h of x equals 9x. It's patently clear on the right side here what my input is, x in all these cases, and what my output is. And you can use whatever kind of, letter label you want to be the output. This is just a very natural way to tell functions apart, and it's very common, and we don't like to overuse that letter y. Alright, so evaluating values in function notation is also quite easy. Let's take a look at the function f of x equals 3x minus 7. Now let's say I want to evaluate this for the number 4. Now I've put the 4 where the x is because I want 4 to be my input. So when I write down the function, I'm going to write the 4 where the x goes because 4 is again my input. So 4 in for x in all places. When you put something into a function, you often just replace for x. Function notation gives you a very clear way of doing this. So I've got my 4's in. Alright, then it's just a matter of simplifying. And I can say that f of 4 equals 5. Listen to me as I say this. When I'm talking about function notation, you read it as f of, whatever number's inside, equals whatever number you get. So in this case, f of 4 equals 5, and 5 must be a point that is on my function. Okay, so now you know how to plug values into functions that are in function notation. Let's try composite functions. So let's let f of x equal 2x minus 4 and g of x equal x squared plus 1. Now let's evaluate f of g of x. Now, please don't get scared. Just like before, whatever is inside those parentheses is my input. So in this case, for the g function, the x is my input. That's just like normal. And for the f function, I'm putting all of the function g of x into f of x. So here, I simply do what I did before. I find the x in the f of x function, and I replace it with g of x instead of replacing it with a number. Well, that's all good and well. Now g of x itself is a function in and of itself. So that same x that same g of x that I just popped in there can also be written as x squared plus 1 because g of x equals this x squared plus 1. So that's how I get away with writing g of x in there and then substituting that with x squared plus 1. Now we've built ourselves a composite function, and the only thing left to do would be to simplify it. I don't mind if you simplify it at this juncture. I just want you to get used to the fact that you can use an entire function as an input into another function. Now let's look at this alternative notation. Often you see what looks like the letter fog here, which is actually f and then a small open circle above the line, g, and then you see x in its own set of parentheses. This means the same as f of g of x. It's just an alternative notation, and I think it's clearer when we write the nesting functions, so that's what I tend to do. But if you run across something that looks like fog in a book, that really means f of g.